In this presentation, we are going to discuss serverless pipelines, a way to automate the interactive mode of working with the big data. We're going to provide some background and then discuss what is the serverless big data analytics pipeline, why do we need pipelines, and how Cloud Button handles serverless pipelines. Actually, the mechanism for serverless pipelines in Cloud Button is workflows. And specifically, we use Argo workflows and Argo events, which are Kubernetes native event-driven workflow mechanisms, to implement these workflows. We will discuss the Argo-based implementation of the Cloud Button serverless pipelines and relate them to the overall Cloud Button architecture. Then we are going to show a small demo and discuss a future work. So let's start with the background. The interactive life cycle of working with big data looks something like this. So let's say we have a data scientist called Alice. The data scientist actually has to do some operations on the dataset instance, which we name data1. It resides in the cloud. The data scientist might have a tool called Notebook. Specifically, many data scientists like to use Jupyter notebooks. So the data scientist defines computations inside the notebook cells. Let's call the computation 1. In this computation, essentially the data scientists want to perform a massively parallel computation on data 1. So she partitions the data, and according to this partitioning, a number of serverless functions are getting executed. Unfortunately, an error has occurred. Maybe it has to do with the partitioning, with the specific partitioning that Alice has done. Maybe the memory allocation per function was incorrect. Maybe the total number of functions was incorrect. But in any case, an error has happened. So Alice thinks, okay, so maybe we can fix the data partitioning and partition the data differently. And then it tries again with a different partitioning, and again we have an error. Okay, so maybe we can try something different. After fast forwarding a number of iterations like this, which are essentially debug iterations, and they might be related to Cloud Button or not related to Cloud Button, Alice gets a debugged notebook. And now when she issues a computation 1, the execution occurs correctly, and data 2 is being created out of data 1 as a result of this massive parallelism. Now Alice moves on with her notebook and creates a Cloud Button based computation 2 that is supposed to work on the data set data 2. So again, it looks similar. Data 3 is created. Perhaps there were some debugging steps similar to what we have in computation 1. Maybe it also happened in computation 2 and computation 3 and so on, but we will omit this. So at this point, Alice can visualize her data. So you see that in the notebook there is some visualization happening, and essentially she has debugged now her notebook, and the data scientist implicitly has defined a simple analytic pipeline. And essentially on event run notebook, two steps are being executed, computation 1 and computation 2. Now this brings us to what is exactly a serverless pipeline. So a serverless pipeline in general is a DAG of computational tasks, directed acyclic graph of computational tasks. These tasks are executed on events such as a new dataset arrival, a clock interrupt, an explicit request by a pipeline owner, a notification by a team member, and so on and so forth. The pipeline executes with no human attendance, and possibly it's subject to overall or per task budget constraints and deadlines. The individual tasks can be either massively parallel or sequential. They can be serverless or serverful. Potentially, these tasks can be executed by different backends, such as, for example, public cloud offerings, and this can happen across multiple clouds. It can be executed by Kubernetes clusters, which can be spread again across multiple clouds, and so on and so forth. Then why do we need pipelines? Of course, we need pipelines for code reuse among data scientists and across teams. We need them for automation because we have long and complex multi-stage computations, and we want these computations to be orchestrated by the engine, which means we want essentially to have a debugged pipeline committed to the cloud and executed in an unattended mode on the server side. We want to be able to compose different pipelines so that they can be combined to handle multi-dataset analytics with datasets arriving asynchronously from different teams. If we have a formal pipeline, then its structure can be used by some optimization that learns from multiple executions of this pipeline, and scheduling of this pipeline can be optimized, and this is important for cost efficiency. To summarize, if we have serverless pipelines as a first-class citizen in Cloud Button, then it becomes a tool to boost the productivity of the data scientists. So let's take a look at the before and after situation. Before serverless pipelines, as we've just described them, and after we introduce serverless pipelines. So let's say we have a team comprising Bob and Alice, and as before, some computations happen. So let's say Bob just creates experimental data set, data 0. Then it runs some massively parallel computation to obtain dataset data 1. At this point, Bob has to tell Alice explicitly, Alice, now the data 1 is ready. You can use it in your notebook now. This is the URI, and Bob has to tell Alice using either Slack or mail or phone, but there is something which is off the grid, basically, some communication that should happen in order for Alice to know that the data is ready for her. So now Alice starts running her notebook, just as we explained earlier, and data 2, data 3 appear in the cloud, and maybe now after Alice visualized data 3 and she's happy with the results, she might need to tell somebody else in the team, let's say Jack, about the data 3, that the data 3 is ready, and Jack can use it, and this can go on and on and on. So in the after situation, we're going to have a slightly different life cycle. After Bob has debugged his notebook, he just exports it as a pipeline into the cloud. Essentially, he pushes his notebook into the cloud, and the notebook will be defined by some YAML document and some Python code. So the same process, but completely asynchronously and independently of Bob's process, happens at the Alice side. Once she has debugged her notebook, she exports it as her pipeline into the cloud. And now let's take a look at Jack. Jack might need to import Bob's pipeline, Alice's pipeline, do some computation of his own, and create, once he debugs it and he's happy about the notebook, he can in turn export it as Bob plus Alice pipeline into the cloud. And now let's say that the data 0 has appeared. Maybe Bob has created it. This is actually an event that would automatically trigger Bob plus Alice pipeline. And then data 1, data 2, data 3 are going to appear, and when data 3 is computed and the last pipeline, the last step in the pipeline is finished, then Jack can be notified that the data 3 is ready for visualization, for further processing, and so on. For example, Jack can get an email with the URI of the bucket where the data 3 is located. So everything here happens completely asynchronously, just when it should happen, just for the duration when it should happen, without human intervention, and essentially the automation is event-driven, and one pipeline, when it terminates, creates an event for another pipeline to start, and we only need to supply an initial event that would trigger the first pipeline in this composite, and then everything else will be taken off in an automated manner. Okay, so now Jack visualizes data 3, and this actually creates a completely new, much more highly automated environment for the team. So this experience in Cloud Button actually is being provided by the execution framework, and it can be viewed as a generalized user experience which doesn't actually require any new programming skills or expertise or knowledge on how to manage workflows. Essentially, we want to have something in the notebook. Then when we have it ready, then we push a button, and this notebook is being created, it's converted into a pipeline and is being pushed into the cloud just similarly to how a parent function is being pushed into the cloud and later used for massively parallel computations. The server side of the pipelines is being handled by the execution engine, and this execution engine is enriched with the serverless workflow management and orchestration functionality, as we will explain shortly. So let's take a look under the hoods. We actually set the goals. We understand why we want, what the pipelines are, why we want pipelines, and how it will change the situation after the pipelines is introduced. So now let's take a look under the hoods and see how we actually implement this in the Cloud Button project. Serverless pipelines in the Cloud Button toolkit are being implemented using the open source CNCF Argo project. CNCF stands for Cloud Native Computer Foundation. It's part of the Linux Foundation. And essentially it's a very large ecosystem of open source projects together creating something which is called Kubernetes native infrastructure. So Argo project specifically comprises 3 sub-projects: Argo Workflows, which is a Kubernetes native workflow management system; Argo Events, which is a Kubernetes native event system that allows to trigger any Kubernetes resource, including Argo Workflow, in response to some event dependency evaluation to true or false. And there is also something which is called Argo CI/CD, but we are not going to talk about it today. So Argo is also the basis of Google's flagship Kubernetes machine learning pipelines project, which is called Kubeflow. Argo Workflow is an instance of an operator design pattern. It comprises a custom resource definition, CRD, called Workflow, and there is a controller which watches custom resources which are instances of workflow CRDs. These CRs, they're essentially YAML files, and CRD is the schema, the grammar of these YAML files. When a new instance of a custom resource, CR, is applied to the Kubernetes API server, Argo Workflow Controller starts a reconciliation cycle between the desired state, as it is specified in that YAML definition of the CR, and the observed state, which are the steps in the workflow that have been executed so far. So let's take a look at the Argo Workflow custom resource example. This is a very simple template. I apologize for the small fonts, but it's really a very simple template, but it will give us the basic idea of how Argo Workflow are defined and what they look like. It's important to notice that this is the under the hood foil. So basically the data scientist is never exposed to this level of details, to these YAMLs. This is all created automatically for the data scientists, and his notebooks are automatically converted into this type of YAML dialect, Argo dialect, that can later be executed by the Argo workflow controllers. So this simple example is about, it's called a diamond. It's about 4 tasks, A, B, C, and D, with task A being the entry point of the task topology, B and C being dependent on A doesn't have dependencies, and D are being dependent on B and C. B and C do not have dependencies among themselves, so they should be executed in parallel. So this YAML definition is, as I said, for the new custom resource, and this new custom resource is called workflow. The YAML definition defines the entry point, which is diamond in this case, and then it defines which type of a workflow is that. In this case, it's a DAG, a directed acyclic graph, and there are two types of constructs in the definition: tasks and templates. So the tasks are names of the steps. So we have tasks A, B, C, and D, and in the specification of each task there is a template to which we will get a little bit later, which essentially should be defined somewhere in the definition as of the workflow, and it defines the parameters of the actual execution of what is actually done by this task. So in this case, we have a task named A that is going to execute template called echo. It has arguments into this template, which is actually a message. And then we have a similar task B. This task has dependencies. There is only one dependency on task A. It executes the same template echo and gets the same input parameters, which is just a message. Now we have task C. Task C is similar to task B. It has a dependency on task A. It executes the same template echo, and it gets the same input parameters. And task D is similar to all these tasks, but it has dependencies on two tasks rather than one task. B and C executes the same template and obtains the same arguments. So really simple. And now we get to the template echo. So you see that we have in its specification what input parameters it receives and what container it executes. So for the container specification, we have image specification and the command that we are going to execute, which is just an echo command. So it would just print a message. So when we execute this workflow, we are going to see A, B, C, D, basically, in that order of dependencies. Everything in Argo, which is executed as a task, is actually a container executed as a pod in Kubernetes and natively orchestrated by Kubernetes. Now, Argo has a very rich set of features. This goes far beyond this simple example. It allows to specify different topologies. It allows to reuse templates, allows to specify secrets, artifacts. It has scripting, it has loops, conditionals, retrying policies, recursion, timeout handling, notification, restrictions, metric collection, even things like cost optimization via node selector, when you can instruct Kubernetes to execute a specific template on, let's say, a cheaper node or a node with some specialized hardware and so on and so forth. So there are many features. There is no point in going over all this list. Believe me, this is one of the most expressive workflow engines out there. Currently it is being used by 57 companies and the community is fast growing. So now let's take a look at Argo events. Essentially, Argo events is an event-driven workflow automation framework. It's another project in Argo project. Um, it helps to trigger any Kubernetes objects such as Argo workflows, serverless workloads such as even OpenWhisk functions, Lambda functions. It can obtain events from a variety of sources like S3, webhook, cron, messaging queues, PubSub, brokers, and so on and so forth. And essentially, via Argo events, you can specify event dependency, and when it evaluates to true, then something is triggered by Argo events. Now, in a nutshell, the main entities in Argo events are gateway controller, sensor controller, and since we're going to talk about sensor triggering Argo workflows, we also will have workflow controller in the picture. So gateway controller watches custom resource definitions for gateways. There is another resource, another custom resource, which is called gateway. So let's say we have defined such custom resource, which we call Bob plus Alice. That would correspond to this composite pipeline that I was describing earlier. Every controller actually watches instances of these custom resources. Sorry, I'm not sure what I did. Okay, so it watches the instance of custom resources. Similarly, sensor controller, for the sensor controller, a custom resource Bob plus Alice is being defined and is being watched by the sensor controller. And now an event happens. An event can be an event, again, coming from any of the 20 plus sources that gateways of Argo events currently know how to deal with. For example, it can be a message on a message queue or an HTTP request, or it can be something that you type in Slack or whatever. Essentially, just this first event needs to get into the gateway controller, and then it passes this event to the sensor, and the sensor controller actually applies the definition of the workflow custom resource for Bob and Alice for the attention of the workflow controller, of the Argo workflow controller. The workflow controller receives an event that a new instance of a workflow has been created and applied to Kubernetes, and then it starts the reconciliation cycle, essentially executing the logic which is specified in this workflow custom resource for Bob and Alice. Now, this is all good. So we have the machinery, but how exactly we can turn a Jupyter notebook into a workflow? So in our solution, in Cloud Button, we use a standard tagging mechanism of Jupyter Notebook to tag cells of the notebook. And cells with the same tag automatically translated into the same template in Argo Workflow YAML. The execution template corresponding to this step is obtained via a standard mechanism of exporting Jupyter Notebook as PyNB file and converting it into the Python code using standard NB converter mechanism. NB convert is customizable, so we extend it to convert the notebook into an Argo workflow template, where steps execute Python code from the tagged cells. Importing one Jupyter notebook into another one is achieved via the standard notebook loader and notebook finder mechanisms. And we add a, so to say, push to the cloud button, such as basically a cloud button specific cell that contains a standard directive to convert tagged cells to steps and templates in the workflow. Order of the steps and step to template relationships are expressed via standard metadata mechanisms of Jupyter Notebook exposed as customized tags. And now it's a demo time.